So the full arch model then, so what is happening here is that you've got some allowance for volatility from the previous P periods to affect the volatility today, and all that happened to the arch 1 model is that volatility from the previous period can feed forward and affect today. Okay, so that is what the equations mean below the second bullet point. Okay, much of this is exactly the same as we saw in the previous slide for the Arch 1 model. Okay, so it's slightly more grotesque mathematically, but it's the same underlying idea. And really, the intuition is that it allows for high values of volatility to follow each other, but also at the same time for low values of volatility to follow each other. Okay, so all that happens though is that for the Arch 1 model, it's volatility from the previous period that feeds forward and affects today, and for the Arch P model, it's volatility from the previous P periods that feeds forward and affects today. But it's the same basic idea. There's some maths here, but all these equations are telling you is it's just precisely this simple idea. The Arch model allows for high values of volatility to follow each other, but also for low values of volatility to follow each other. So in terms of Arch and Garch then, so Arch and Garch models have spawned a sort of cottage industry and fairly tedious financial econometrics. So there's various names that are often bandied about, so things like E-Garch, M-Garch, S-Garch. So they're all basically variations of a theme. Okay, the basic ideas really are contained within Arch and then generalization to Garch. So these are a little bit difficult to spell and to pronounce. Here goes. So Arch stands for autoregressive conditional heteroscedasticity, and Garch stands for generalized autoregressive conditional heteroscedasticity. So as the name suggests, Garch is a generalization of Arch that allows for slightly richer behavior in volatility. Okay, and so it's sort of natural here to start with Arch and then consider the slightly more complex Garch model. And then what you can sort of see here is that in some sense Garch is really almost the point of genesis here, in that there are various further extensions of Garch, such as E-Garch, M-Garch, S-Garch, T-Garch, all sorts of things. Okay, but Garch is really the crucial building block for the rest of this class of models. Okay, so it makes sense from in terms of the theory, not just the applications, to study Garch. So I wanted here to sort of try and give an idiot's guide to time series, precisely because we're going to focus on this module on the subject of financial time series, which is a small subset of what there is out there. Now it's a hard subject, but precisely because our focus is going to be so narrow, firstly on financial time series, and secondly on just on Arch-Garch models, that actually this is going to make something that's highly complex very straightforward. Okay, so there's a whole statistical subject of time series that is inherently specialist. Now, one thing that is easy to miss here is that financial time series is a little less specialist, so it's easier and more doable and more practical, so you shouldn't be scared of this, but it is a subject in its own right. Okay, you can't study time series and then take it for granted that you're automatically going to know how to do financial time series modeling. And as part of this, financial time series is very different from the regular ARMA time series that people might study on a different course. And the ARMA time series is really a mainstream area of mathematics and statistics. Financial time series is inherently specialist. So what you have here is that the Arch model is an autoregressive model for volatility, and the Garch model is an autoregressive moving average model for volatility. So just to try and put that into context, if you don't know what these terms mean, don't worry. Arch 1 model then, so you start with the Black-Scholes model, and under this model the volatility is constant, and again this is at odds with real stock market data. And then the Garch 1.1 model is a slightly more advanced partial fix to this problem compared to the Arch 1.1 model. Okay, the basic idea is that volatility from the previous time period can feed forward and affect today. So this enables then high values of volatility to follow each other and low values of volatility to follow each other. So if you look at this fourth equation, then sigma squared t equals alpha naught plus alpha 1 u squared t minus 1 plus beta 1 sigma squared t minus 1. So this is just the previous time period that is feeding forward and affected today, and it's just a slightly more complicated way of guaranteeing that you can have high values of volatility following each other and low values of volatility following each other. That is essentially all you need, and all that is happening here, if you wanted the sort of slightly more technical description, is that this is a ARMA model for volatility to achieve this simple aim, so that you might have high values of volatility that follow each other and low values of volatility that follow each other. Okay, that is essentially all you need for this course in terms of what Arch and Garch do. You can have high values of volatility that follow each other and low values of volatility that follow each other. So the general Garch PQ model then, so it's a slightly harder equation, but it's the same basic idea. Again, you've got high values of volatility that can follow each other and low values of volatility that can follow each other to match this observation that this effect happens on real markets, and all that you have here is just a slightly different mechanism by which this is brought to bear. So what you have here, you have a larger ARMA model to produce this effect whereby high and low values of volatility can cluster together. The P bit of the Garch model refers to the Arch bit, and then it's the Q bit, which is the Garch bit, the added extra. So the first P terms here after the alpha naught term is the Arch bit, and then the next Q terms are the Garch bit, and that is the reason for the mathematical terminology Garch PQ. So the first P bits are the Arch bit, the next Q bits are the Garch bit. Now, unhappily, this is how it's usually written down mathematically, but the R coding for this is actually the other way around. Okay, so this is a pain, and I think this is sort of suboptimal in terms of the R coding, but it actually makes it easier if you can remember that R gets us the wrong way around and is a bit quirky and counterintuitive. So I wanted here to try and emphasize what these things are doing physically. So choosing the order of an Arch-Garch model is difficult, and there are several different approaches. It's often simplest to just assume that both Arch and Garch effects are present. Just use the first order model. So this would be, if you're looking at daily data, this might mean that volatility from yesterday feeds forward and affects today, for instance. So this often makes good financial sense and has an interpretation attached to it. You can also choose the order to coincide with certain time periods. So if you had, say, an Arch 5 term, this might mean that volatility from the previous trading week feeds forward and affects today. Again, this can make good financial sense given the context. You can also use t-test to determine the order, similar to t-test in regression, and there's a worked example on this later in the lecture. You could also choose the model with the lowest Schwartz criterion, and this is perhaps the most advanced approach considered in these set of lectures. So this is similar to advanced approaches in computer science and Bayesian statistics, and the idea is that if you choose the lowest Schwartz criterion value, or BIC value, this in fact chooses the model with the highest probability of being correct. So the idea is that physically and financially these things can make a good deal of sense if you choose the order of the Arch-Garch model to coincide with certain time intervals. So there's a sort of non-exhaustive list here. Okay, I don't want to overdo it, but just try and give you a flavour of what can go on. So if you've got daily data, an order 1 model would mean that volatility from yesterday affects today. An order 5 model would mean that volatility from the last trading week affects today. An order 10 model would mean that the volatility from the last 2 weeks feeds forward and affects today. Weekly data, so order 1 model might mean that volatility from the last week affects this week. An order 4 model might mean that volatility from the last month affects this week. For monthly data, an order 3 model might mean that volatility from the last quarter affects this month. An order 12 model might mean that volatility from the last year affects this quarter. And if you've got quarterly data, you might get that an order 4 model would mean that volatility from the last year affects this quarter. Okay, so these things are not necessarily the most exciting bit of lectures you'll ever see, but they are designed to make good financial sense, and there's a sort of believable financial mechanism here to generate these models derived from the human calendar. I wanted here to sort of discuss an example with respect to cryptocurrency data. So other possibilities are, of course, available. Okay, but I just wanted to discuss how you might model cryptocurrency data using the Garch model. So there's two main possibilities here. So if you've got daily data, you could use a Garch 1.1 model. So the assumption here would be that a low order model, and indeed the lowest possible order model, might be sufficient to give a good description of volatility correlations on real markets. However, this is necessarily going to be imperfect. Okay, so just because you've got a hard statistical model that you're applying to your data, don't think that this will give a completely precise 100% description of volatility fluctuations on this market. And then another alternative might be if you're looking at daily price data. Since currency and cryptocurrency markets trade 7 days a week, the interpretation of this model would be that volatility from the previous 7 days, so the previous week, continues to feed forward and affect today. So again, this has a sort of believable financial mechanism attached to this, derived from the human calendar. Okay, lots and lots of different possibilities. Certainly I think these are the most obvious ones to think of with respect to dissertations, and go through examples of these later in the lecture. So in terms of Arch-Garch modelling in R then, so the easiest way to fit Arch-Garch models in R is to use something called a T-series package. T-series, as you might guess, just means time series, so this thing is deliberately named. So this fits a conditionally normally distributed model to the mean corrected log return series. So it's possible that more advanced Arch-Garch models can be fitted, and other packages exist, things like the F-Garch package and the RU-Garch package. This is something I've set for coursework assignments in the past, and is something that past MSc dissertation students of mine have looked at. It's also possible that fancier Arch-Garch models may be required, especially for cryptocurrency applications, on occasion to variously account for autocorrelation in the return series. So the recent paper here published by my former colleague Paraskevi Katsiampa, and also you might want to account for the fact that you can have heavier tails than the conditional normal distributions in the Garch model, so have something like a student T distribution. Certainly the second item here is very common for generic asset price return modelling. Okay, but having said all this, these Arch and certainly the Garch models are a natural starting point and a gateway to something ultimately more complex. So Arch-Garch modelling using T-series then. So the basic command is Garch, even if you fit a purely Arch model without any Garch terms. So one thing I ought to also emphasize here is that T-series gets this thing the wrong way around. So the notation used in R is the opposite way around to the conventional mathematical notation. So this is a bit of a pain and isn't very well written. Okay, but precisely because this is so quirky, I think this actually makes it easier to remember what's going on. So the basic command is Garch applied to a d-meaned log return series here called X, and the order QP. This is the opposite way round to how you usually write down the Garch model mathematically. So in R it calls it Garch QP. Mathematically you normally write this down as Garch PQ. So just to re-emphasize then that X has to be a d-meaned log return series. So that might sound hard, but it's actually really straightforward. You just have to subtract the mean from the log return series, and the T-series ordering gets the Garch PQ bit the wrong way round. Okay, so this is a bit of a pain. Okay, but as I said before, precisely because this is so quirky and a little bit imperfect, it actually makes it easier to remember and to ultimately use.